So we finish this slide. Yeah. Before I go to the next slide, I want to ask you one question. First, I recall the point. This slide, we look at the linearity principle or superposition principle. Yeah. In order to make this principle work, the first condition, we should have a linear homogeneous ODE. Yeah. Linear, yeah. So you know the meaning of linear, right? So what is an linear ODE? Our first slide, we explained, 3 rules. That homogeneous, that's 0. Right-hand side, 0. Yeah, homogeneous. Yeah. Under these 2 conditions, then we have the linearity principle. Yeah, you can apply. So specifically, what do you mean linearity principle, right? Yeah, specifically to apply the linearity. So the linearity principle works in this situation. If we have y1, y2, both solutions of this ODE, then we do linear combination. So this C1, Y1 plus C2, Y2, this is this structure, we call it a linear combination. Okay? Any linear combination of 2 solutions is also a solution, another solution. Yeah. And here you can see this solution is more general. Why? Because C1, C2, 2 constant. We have freedom to choose C1, C2, more general. Yeah. Yeah. All right, so that's the linearity principle. Then this side, if we drop this homogeneous condition, okay? Yeah. So we want to think about, we keep the linear condition, but we drop homogeneous condition. Okay? If we do that, so in this example, right-hand side, it is 1, then we want to show the sum of y1, y2. Here, we have y1, we have y2. And the sum of y1, y2, y3, you can see, y3 does not satisfy our original ODE. So y3 is not a solution of the original equation because it is not homogeneous. Okay? Yeah. So that's what we covered last time. All right. Yeah. Here, I want to ask you, because there is an interesting question I want to ask you before I move to the next slide. So what's that question? All right. The sum of y1, y2 is not a solution of the original ODE, but how much is the difference? Look at the difference. Okay? Original ODE, right-hand side, 1, sum of these 2 solutions, right-hand side 2. Although different, but there is a possibility we can bridge the gap, right? Yeah? Because it's a constant. First, they are both constant. Just the constant values are different. Here, my question is, can we combine y1, y2 in a certain special way such that when we add them up, we get a solution? Can you see that? Yeah. We combine y1, y2. Yeah. But right now, when we combine in some arbitrary way, we cannot put the constant part right. Now my question is, can we apply some special operation to combine 1, 1, 2? Look at the way we combine 1, linear combination way. Yeah. So here, linear combination way won't work, but can we modify the linear combination way slightly to make it work? Yeah. Here, yeah. Because here, not very complicated. Not very complicated. So I ask you, yeah, if you can see that. Yeah, because sometimes, think about it, sometimes you have the non-homogeneous and especially the, non-homogeneous. You want to combine, right? Two solutions. Yeah, you may want to do that, right? Yeah. All right. So here, let me introduce a new special operation, different from linear combination, but we modify slightly. All right. Now I want to talk about a new operation called linear interpolation concept. Linear interpolation, all right? Yeah. So, linear interpolation concept. Okay, yeah. Another interesting concept. Okay, so what's that? Yeah, let me explain. What do you mean, linear interpolation? Let me draw a graph to explain this concept. Suppose you have 2 points. A point here, another point, B point there. Okay, 2 different points. Now, we want to do linear interpolation of these 2 points, A and B. Okay, all right. We connect. We draw straight line segment connecting these 2 points. Line segment. Okay? Yeah. So any points on this line segment between A and B, we call it linear interpolation. Okay? Linear interpolation. But we need to write equation for it, right? Yeah. Yeah. So here I draw the graph. But when you work on this, when you use linear interpolation to do some work, you need an expression of linear interpolation, right? Yeah. You need a formula for linear interpolation. Yeah. Here, let me write the formula. A, we take A. We also take a B. We need to put appropriate coefficient for A, also appropriate coefficient for B. Yeah. But the sum of these 2 coefficients, sum of these 2 must be 1. Must be 1. Okay? Yeah, let me write this way. Yeah, so many times people use lambda as the, parameter to control the interpolation location between A and B. All right. For example, lambda times A plus 1 minus lambda times B. How about that? Lambda, certain parameter, okay? Yeah. Lambda parameter multiplies A coordinates. Here, A means A coordinates, okay? Yeah. Then, parenthesis, 1 minus multiply that B coordinates. Yeah. Look at the sum. Sum of these two coefficients equals 1. Okay? Yeah. That's what we call it, interpolation. Sum of it. If it's not equal to 1, that's linear combination. Okay? Linear combination, sum of 2 coefficients, could be arbitrary numbers. But here, the sum of the two coefficients must be 1, linear interpolation. And especially when you select the points, if the points on the line segment between A and B, so you have 0 less than or equal to lambda less than or equal to 1. Okay? Yeah? The value of lambda must be between 0 and 1. And when lambda takes 1, when lambda takes 1, you are at the A point. When lambda takes 0, you are at the B point. 2 endpoints. 0 and 1, 2 endpoints. Okay? All right. So this is a linear interpolation concept.
Is the sum of lambda, that entire thing has to equal 1? That entire line? Lambda A plus 1 minus lambda times B has to equal 1?
The sum of the coefficients.
The coefficients. Okay.
Only coefficients, not A, B. Yeah, coefficients. Okay? Yeah, coefficients. All right. Yeah. Now, with this preparation, now I want to move here. When we combine y1 is a solution, y2 is a solution, now we want to do linear interpolation of y1, y2. How about that? Yeah. So what do we do? This time, our y3 equals lambda y1 plus 1 minus lambda y2. Okay? Then you plug in. Okay? Yeah. Then you plug in. Okay? Yeah. y double prime y3 equals lambda y1 double prime plus 1 minus lambda y2 double prime. Okay? Then you add up y3 double prime plus y3 equals lambda y1 double prime plus y1 plus 1 minus lambda y2 double prime plus y2. y1 double prime plus 1 equals 1, right? So you get a lambda plus y2 double prime plus y2, also 1, right? So you plus 1. Answer is 1. See? Yeah. In this way, your y3, if your y3 is a linear interpolation of the two solutions, y1, y2, you still get a solution. See? How about that? Interesting, right? Yeah? Yeah? Something useful. So this concept, useful linear combination. Yeah. All right. Then, after this, so now, I assume you understand this concept at this point. Can you see something related to one of the homework questions? Homework assignment, is there something related to things like this? How to start? Oh, yeah, all right. Yeah. All right. In our homework question, all right, part C. Part C, I'll give you 2 questions. The first question in part C, walking from A to B, okay? A, I give you coordinates. B, I also give you coordinates, okay? Walking from A to B, then there is an equation given, x, y, z, okay? X, y, z given, all right. So now you need to calculate rate of change from A move to B. Okay? Now, because You need to draw a line segment connecting A and B. Is it linear interpolation? Use linear interpolation. When you draw A and B, you need to consider how to represent a point between A and B, right? Using certain parameter. You use linear interpolation. So you can get an equation. You can get a parametric equation connecting A and B. AB given, okay? The coordinates, AB, X, Y, Z, AB given coordinates. Yeah, so you get a parametric equation of the line segment connecting A and B. Then you apply chain rule, you can calculate rate of change. Partial derivative, chain rule. All right, homework question related to this concept. Okay, yeah. Don't forget. Otherwise, so I'm afraid some students may not know how to represent a point moving from A to B. Right? Yeah. Here, you have it. Okay? Yeah. All right. Yeah. But although I give you 2 weeks, the duration total 2 weeks, but you need to work on it. Do not delay too long. All right? Yes. Yeah. All right. Yeah. So let's move to the next slide. Particular solutions for second-order linear non-homogeneous ODEs. Right. Standard form, this time non-homogeneous. So the right-hand side, we have an R function, R of X function. Yeah. Sometimes we consider initial value problem, but sometimes we do not consider. Yeah. All right. So this is the standard form. Yeah. All right. If we are given initial condition, so we should have 2 initial conditions. One on the initial function value, another on the initial derivative value. Otherwise, we cannot fix all the constants. Yeah. Because we may have 2 constants. So we need 2 initial conditions to find out 2 constants. Yeah. All right. Next, let's look at how to find a general solution. Yeah. First, because first we want to find we don't look at the initial conditions. First, we ignore initial conditions. Okay? We want to solve a general solution for the standard solution, so standard form. Yeah. All right. We need some idea, so we revisit old example. Yeah. This simple example. Yeah. We try to do experiment on this example to give us some idea that we can use to solve this general form. Yeah. All right. In this simple one, by observation, we can see. Can you see a simple solution here? Yeah. Because sometimes, for simple equation, we want to use our eyes to find a simple solution here. Okay. Look at when y equals 1 is the solution. Yeah, double prime 0. So 1. Yeah. That's the. Yeah. So we call it this. This is a solution. So we call it. It is a particular solution. Just one special solution, particular solution. Yeah. But it is useful. Yeah. One particular solution is useful to help us to solve non-homogeneous ODE. Yeah. So let's move to the next step. How to use this particular solution. All right. We use y0 to know this particular solution. So this equation is satisfied, right? Yeah, satisfied. All right. Then our goal, we want to find the general solution of this one. But we only have a particular solution. Okay? Yeah. So here, the logic. Yeah. Currently, we have a particular solution here. Yeah. But our goal here, find the general solutions, yeah, because general solutions containing parameters C1, C2, right? Yeah, general solution C1, C2, yeah, general solution. All right, yeah. So it's different, yeah, but they are closely related. They're closely related. All right, yeah. So the relationship. Consider a new solution. Yeah, here, really important. Little u equals y minus y corresponds to the general solution. Okay, y corresponds to a general solution. Y minus the current particular solution, y0. Let us use y back in the original ODE and see what do we get. Okay, let's use this u. You can see if you do the simple operation, you can see, yeah, because u equals the difference of y and y0. Then you take difference. Original equation, this special equation, you take the difference. Right hand side, 1 minus 1 gone. Left hand side, double prime part, you get a u double prime. Y minus y0, you get a u. So at the end, you will get a u double prime plus u equals 0, homogeneous. See? When you take a difference from non-homogeneous to homogeneous, the only difference is you use a general solution to subtract a particular solution. Then you get a general solution for the homogeneous version of the original equation. That's the, the property we observed. Here, we studied the property. This property is important. This property bridges the difference between homogeneous version of ODE and a non-homogeneous of ODE. Bridge that difference. Okay? That's why it's important. All right. Yeah. Now, that's why the first step, we solve the homogeneous version. Yeah. Although it's different from our original question, but it is useful. The result of the homogeneous version of the equation will be used when we write the final non-homogeneous solutions, general solutions. All right. With a general solution, now we need to get it. What's the general solution? Yeah, we did it once. Remember, in our module 1, part C, yeah, solving PDE, simplest PDE. So I did this. Yeah. Yeah. So here I just write it directly. Okay, you do not need to go back to, look at your notes. Yeah. C1 times cosine x plus C2 times sine. Remember, I used the Euler's formula I. How to cancel I. Remember, we did in class. How to get around. Remove that I thing, right? Yeah. Capital A, capital B, plus, minus. Yeah. Yeah. All right. So the final general solution of this homogeneous, that's this one. Okay. Yeah. All right. Yeah. Next, we can move to the general solution immediately. What's the general solution of that? Yeah. Yeah. General solution. Yeah. So let me erase. Yeah. All right, general solution plus 1. See, the homogeneous general solution plus the particular solution. Because you do the subtraction to get a homogeneous function for the solution of the homogeneous version. Now, you want to go back to the non-homogeneous solution. So you add this particular solution back to your homogeneous general solution. So you get a general solution of the non-homogeneous. Here, can we do the same thing here? Although that's a simple example, but we can easily generalize to the standard form. Easily, yeah. All right. First, we want to solve the corresponding homogeneous ODE, that is this version. Okay? Yeah. How to solve, that's another question. Okay? How to solve it, it's not easy. It's not easy. Yeah. Because for the general P function, general Q function, it could be very hard. Arbitrary P function, arbitrary Q function, it could be very hard. We can only solve relatively simple P function and Q function. Relatively simple. Arbitrary, you know. Yeah. Yeah. So for the arbitrary, yeah, so later I will talk about. So because yeah, later I need to find a chance to talk about numerical solution. Numerical solution. Yeah. The reason is the formula way solution like this, we call it an analytic solution because you have formulas. Okay, you have concrete formulas, so we call it analytic solution. In the real world situation, to get analytic solution, only very small portion of the problems you have analytic solution. Yeah. Large for most of the application problems, you cannot get an analytic solution. So you have to take the numerical solution. Yeah. But now look, our computer is very powerful. So numerical solution, we need to write program. Okay. Yeah. Implement. Yep. So yeah. So we describe our functions using the numerical values. No formulas, but you have the values of the function. Okay? Yeah? All right. So for example, function usually you, like it's a curve, right? Yeah. But most of the time in the real world situation, you will not get a formula for this function. Okay? What you get is the numerical values on the sample points. So we call it, sampling. Okay? You do the sampling. Yeah. And you have the function values on all those sample points. That's what you can get in the real world situation. Okay? Yeah. But that's good enough. That's good enough. Okay? Yeah. So for this kind of understanding, you can see numerical approximation concept is very important in real world problem solving. Yeah. All right. So I try to find one or two parts. Yeah. Yeah. One or two parts. Talk about numerical solutions. Yeah. This semester. Yeah. Probably after midterm. After midterm, I try to find one or two class sessions. Yeah. All right. Yeah. So now you know, yeah, you know the process. Okay, basic process. Okay, yeah. All right. So next, now we need to work on the solutions. So that's pretty hard. Yeah. Work on the we try to solve even the second order. So you can see even the second order homogeneous linear ODE, yeah, still pretty hard. Yeah. All right. So 8.2, we need to study some two important concepts. Basis concept, linear independence concept. Here you can see these two concepts closely related to linear algebra. Linear algebra, yeah? Yeah. Based on my experience of the previous 2 semesters, so most students, it looks like they did not quite like linear algebra. They were not familiar with linear algebra, yeah. But we need to. Yeah. So for this class, we need to apply some knowledge of linear algebra, but not very deep, not very hard. Yeah. All right. So let's look at the concept. The form of general solution, initial value problem. Yeah. Yeah. We consider a particular solution. Then, yeah, so we use the same way. In the previous slide, yeah. So we consider u equals y minus y0. Then u is the solution of the homogeneous version of the original equation. Okay, homogeneous version of it. Yeah. All right. Need to find 2 different solutions. Yeah. So here. That's the question. Next, we need to consider the first part, second part, okay? The first part, we solve the homogeneous version of the original ODE. Second half, we need to find this y0, particular solution of the original non-homogeneous ODE. Okay? Yeah. Two steps. Yeah. All right. For the first step, now we need to study completely the first step. Yeah. Here, I mentioned there's 2 different solutions. Okay. Then, here, you know the meaning of 2 different solutions. Now, you know the meaning, okay? Yeah. But, to understand the point correctly, it's not enough. So if you just use 2 different solutions, it may not be enough. Okay? Yeah. Here, the problem is, all right, there is a problem. Although you have 2 different solutions, but you may not get what you want. Okay. All right? For example, you have y1 solution and a y2 solution. But your y2 equals 3y1. Okay? y2 happens to be 3 times of y1, although they are different. You cannot say they are the same solution, right? They're different. But if you use this y1, y2, you cannot get what you want. So what do you mean, what do you want? We want to get a general solution for the homogeneous ODE, right? General solution. But if you use this kind of y1, y2, you cannot get all the general solution. You can only get a small portion of general solution, but not all. You miss a lot. So this kind of y1, y2 won't work, although they are 2 different. Okay? Yeah. So that's the problem here. Yeah. So we need to understand for what kind of y1, y2 we can make it work. Okay? Make it work means we do not miss any solution in our general solution. Our general solution covers all the possible solutions. That's what we want to get. We don't want to miss any part of the solutions, right? Well, so that's the point. Okay? All right. Yeah, so here. What conditions do we need for y1, y2 in order to make our general solution cover all the possible solutions? Yeah. How different they should be. You said different, right? But that kind of difference, still the difference too small. The difference is not that big. We want a big difference, not small difference. Yeah. Because y1, y2, if the difference is only 3-to-1 ratio, then too close, right? Too close. Yeah. All right? So, yeah. Actually, what do we want? We want these two solutions are fundamentally different. Fundamentally different. Okay? Yeah. Yeah. All right. Consider a special case. Yeah, so here, k times, right? Like that. All right? This does not help because ky1 is automatically a solution of the homogeneous. And when you use these two, you can only get constant multiple of y1 solution, but you won't get many other solutions. You won't get many other solutions. Okay, all right. Now, we need a solution y2 with y2 not equal to any k multiple of y1. We do not allow it. Okay? y2 equals k multiple of y1. The similarity is too strong. The similarity too strong. So we want to reduce the similarity. Okay? Yeah. So we do not allow y2 equals k y1 for any k. Okay? Not just for 1k, for any constant k. We do not allow it. Okay? All right. For any constant k. Yeah. That means y1 and y2 must be linearly independent. Here we need to use this linearly independent concept. Because when y2 equals k y1, these two functions are linearly dependent. Linearly dependent. Yeah. If you recall a little bit linear algebra, here you need to recall a little bit. Yeah. Because this class we cannot spend a lot of time on linear algebra. Okay? Yeah. So if you recall linear algebra, all right, a little bit, if y2 equals k y1, you can write a linear equation k y1 minus y2 equals 0. Okay? Yeah. You can write this equation. That these two functions are linearly dependent. See? Yeah. K times y1 minus y2 equals 0. Yeah. This equation tells us these two functions are linearly dependent. Yeah. We do not allow it to happen. So we want to have these two functions must be linearly independent. So we need to study this concept, linearly independent concept. And together, linear dependent concept. Yeah. All right. Yeah. We say, yeah, that another related concept, the basis concept. We say that such y, 1, y2. Yeah. What such y? So y1, y2 linearly independent, such, okay? So suppose we have the independence between y1 and y2, then such y1, y2 form a basis of the solutions of the equation. So we have this basis concept. Okay? Now, let me explain this sentence. The second one. Such y1, y2. What's such? Okay? Such means this linearly independent property. Okay? Assume that. Linearly independent property. With this linearly independent property between these two functions. Now, these two functions can be used to represent the general solution covering all the possible solutions of the homogeneous ODE. That's the conclusion. These two functions are good enough. These two, because they are fundamentally different. Linearly independent means these two functions are fundamentally different. The difference is big enough. Okay? All right. So when these two functions are fundamentally different, we can use linear combination of these two functions. This time we can use a linear combination. Linear combination of these two functions, we can cover for our general solution. The general solution in this form will cover all the possible solutions of the original homogeneous ODE. We won't miss anyone. That's pretty good, right? Yeah, we won't miss anyone. It can be proved. Okay? Yeah, in this class, we won't prove. I just give you the result. Yeah. It can be proved. Yeah. When we write our general solution in this way, linear combination of y1, y2, but y1, y2 must be linearly independent. Then we cover all possible solutions of the original homogeneous. That's why it's important, right? Yeah. So that's why this concept is important. Okay? Yeah. Linear independence. Yeah. So then the basis. Yeah. But I also need to talk about the basis concept. Yeah. Another important concept. Yeah. In linear algebra, you learn the basis concept. But here, we need to use this basis concept. Yeah. So these two functions form a basis. What's the meaning? The basis means any solution of the original homogeneous ODE can be represented as a linear combination of these two functions. That's the basis. That's how people use this basis concept. Well, these two functions, when they form a basis, linear combination can cover, all the solutions we want to find. All right, yeah, Christian, yeah, probably dropped the line. Yeah. All right, yeah, the basis concept. Okay, all right, yeah. So let me move to the next slide. Yeah, before the break, I need to cover another slide before the break. Yeah, I spent too much time. Yeah. All right, basis and linear independence. Yeah. Understand the basis. Yeah. A basis should have certain fundamental role in forming a solution of the equation. Yeah. Fundamental system. Yeah. So we call it another name for this basis. Fundamental system. It's a system. Yeah. All right. Fundamental. All right. A basis contains certain number of elements. Yeah. So a basis could be from 1 through infinity. Could be infinity. Infinite many number of functions you use as basis. And that's possible. Yeah. But in this class, we only use finite many functions. Yeah. Yeah. All right. Dimension. Yeah. So we use dimension. Basis, if your basis have two functions, we call it dimension 2. Okay. 3 basis functions, dimension 3, and so on. Yeah. All right. For any solution, it is sufficient to use the elements inside the basis to represent it, linear combination. How to represent any solution, we can use the linear combination of certain number of elements inside the basis. So that's why finding the basis functions is important. Yeah. Solving this kind of ODE. The way to represent solution is linear combination of the elements in the basis. Yeah. All right. Yeah. So all these are important points. Yeah. All right. In this problem, the dimension of a basis 2. Yeah. Y1, Y2. Yeah. Here you can see. Yeah. Why only Y1, Y2? We do not have Y3. Yeah. Independent. Y3. If we want to have Y3, we need to require Y3 must be independent of Y1, Y2. Yeah. But we will not have independent Y3. Yeah. The reason is we are working on second order ODE. Second order ODE, 2 basis functions. Third order ODE, 3 basis functions, and so on. Nth order ODE, n basis functions. So here, second order, so our basis, the dimension of a basis is 2. All right. The 2 elements of the basis must be linearly independent. Yeah. Linearly independent. Okay. All right. The basic properties. Yeah. All right. Question: how to understand linear independence? Yeah. All right. Let me pause a little bit. Yeah, because this concept is important. Yeah. So let us take a break, and you come back. We will start the second half at 7:10. 7:10. Yeah. So a few minutes before 7, but yeah. So 10. We start at 7:10. We talk about the linear independence concept.